Oh shit, my. All right, boom, boom. All right, boom. I'm live. Let's see if we can get a couple people to show up to this super random live stream. In the meantime, I'm gonna post this link. So wait for a couple people to hopefully show up. We're gonna have a little fun. uh, I am posting to socials that this stream is live. I cannot see the chat. Just a heads up. Beautiful. I need a button where I just click and it just like sends the update to all social media. Going one by one is it's a little tedious. Here we go. Bada bing. I gotta click view. Bada bing. Wait, did I reply to that or whatever? Whatever. All right, and then final place to put it is on Discord. We got 27 people in here. What's up? Hakuna David, Andy Skit, John Blunt, Kevin Duran, Boxhead, what's good? And David again. Who said watching while preparing for an interview? Shouts to John Blunt. Best wishes to you, my friend. I'm gonna begin this in 1 second. I just need to post on the last place that the stream is live. All right. All right. Okay, I think I'm ready now. Okay, so we got a question from David. What exactly are you trying to code? What a great question, and what a great segue actually into getting this stream started. So I uh am a very sporadic person. I just have random ideas from time to time. In fact, I probably have 30 ideas I want to try at every given moment. But there's only 24 hours in the day, and most of the ideas that I want to do, they take a lot of time, a lot of time to complete. However, there's one idea that's been on my mind for a few years now. What's up, Outer Cloud? Shouts Outer Cloud. Welcome in. There's an idea that's been on my mind for a couple years now, and I'm a huge biology fan. I love biology. Um, Wait, hold on. Oh, I forgot to turn off DVR. Oh no. Can I turn off DVR when the stream already started? I hate DVR because people get lost sometimes. Even I'm lost. Damn it, I forgot to turn off DVR. Oh, here we go. I can turn it off live. Perfect. Okay. DVR is turned off. Okay, cool, cool, cool. Where was I? So I've been a huge fan of biology for many years. In fact, if things didn't work out with computer science, I'd probably be a biologist. But anyways, I'm rambling. Biology is really fascinating, and I just had this. I for some reason every like few months I go on this like binge of learning the core mechanics of like microbiology, And this last binge, like a few weeks ago, I was like, wait a second. If you stop and think about it for a second, right? Everything that we know, everything that in our existence is is based on like DNA essentially, or at least like life. Life itself is based on DNA, right? Where there are four nucleotides, A, C, G, and T, that are stringed together. Millions and millions and millions of pairs are stringed together that are essentially like a memory card, in which somehow, some way, life has figured out a way to like read this memory card and create complex life like humans, that we're able to do everything we do. We don't need to be charged to a wall or anything like that. And when you think about that, you're like, wait a second. So you can take something that is simple as DNA, and extract it to create something as complex as human beings. You must be able to like use this some way to create intelligence. This was the initial thought. Um, and funny enough, some of the early neural network stuff was inspired by how our brains work. As you know, neural networks are literally, they're called artificial neural networks, ANN, because they are inspired by our brains, at least from what we know of it so far. And you connect them all together, then they will create relations that we don't fully understand at this moment, but you have this black box that can do very useful things. Did you look at the collaboration aspect I suggested on Discord? Hakuna, uh, are you howdy? Are you howdy on the Discord, Hakuna? I think I did look at the one that you were saying, but I had, by the point that you had posted that, I had found like another direction to go, and so we'll get into that in a little bit. Hello to Legacy of 2009, welcome. So anyway, so artificial neural networks are inspired by the human brain, right? That was some of the early research. They thought that, hey, we use our brain as intelligence to pattern recognize, et cetera, et cetera. Why can't we create a digital version of that in the computer, and maybe we can get some results from that? And they were right. You know, some of the early researchers like Jeff Hinton and Jan LeCun, et cetera, et cetera, they were right with their hypothesis. And as you interface with ChatGPT, you interface with some of the image generators and stuff like that. A lot of classifiers that you probably don't even know that you interface with that are AI and are powered by neural networks. The hypothesis turned out to be very, very true and very monumental to the field of AI. However, I, I'm not like, I would never compare myself to any expert artificial intelligence researcher whatsoever. But I have been dabbling in artificial intelligence since I was really young, way before neural networks are even a thing. I would just dabble in like state machines and things of that nature, right? Um, and I would say that I have a lot of passion for AI, and I've utilized a lot of neural networks and built a lot of neural networks from scratch in my days. And there's one thing that I have always found is an issue with artificial neural networks, and that is that it, well, one, it's not really intuitive to understand what's going on. It is very much a black box. And then the second thing is that it seems like it's only good at doing very specific things, and then the starting conditions of the thing is like very important. There's a few different issues. Where am I going with all this? Who is the guy that fights Genzo in the original Jabrils from 4 years ago? Box said, "I promise I'm gonna get to all the hacksware questions. Let me just get this out of the way, and then introduce the research I've been doing over the past couple weeks, and then towards the end, I'll answer all of your hacksware questions. I promise." Dan, yo, what's up? Welcome joining us. Sounds close to your research. I would love to hear more about your research, Mr. Panda. I would love to hear about it. But anyways, getting back to what I was saying, um, come full circle, right? Artificial neural networks has brought us a lot of value in designing computational problem solvers inspired by the design of our brains, right? Our organism brains, right? Not just humans, just organisms in general. But my question is, what if you take a step back, right? What if you take a step back and instead you utilize like the building blocks of life itself to form intelligence, right? Because before the brain, you have DNA, right? You don't have a brain without DNA. And so that brings us to my that brings us to my project. Sorry, I don't have all. I should have had all this uh, laid out as a presentation, but this is kind of a whim. That brings us to, come on, transition. Oops. This brings us to my project idea. I'm calling it DOT. It's kind of I just came up with it on the whim. Stands for DNA optimized tasks, right? And you can see a bit of the different structure here for how an artificial neural network works. Um, you have your inputs, you have your outputs. This is going to be true for all networks. I mean, of all solvers, right? You need some relation between the input and output. And wait, where is my chat? My chat's here. And the difference really here is that, and there's many different forms of artificial neural networks, right? There's like a feed forward, there's neat, there's reinforcement, there's so many different types, but like the basic concept is that you have this black box here that is fit in between the inputs and the outputs, and you kind of just feed forward that data, and you have weights. There are some weightless models. I don't know too much about those, but you have some weights that you adjust that essentially acts as like the saving the state, right? And then, some of them you can back prop. That's how you can update the weights. Some of them you can do genetic algorithms, et cetera, et cetera. However, what's different with this new approach is that, yes, this is still a black box, but this is heavily inspired by how our body, how all organisms create intelligence, right? Or operate based on intelligence. So you have receptors here. This is the first layer. You feed the inputs directly into what I call external receptors. And then the external receptors then go into promoter activation. And this gets really technical. I'm not going to give you a whole biology 101, but it goes into promoter activations, which is inspired by our real biology. And then these promoters, they create proteins. They produce proteins, and then the proteins then will activate internal receptors. And the internal receptors are connected to the output, right? And there's going to be some carryover. Some internal receptors will activate promoters that then gets fed into the next loop of the run, which you can see here, right? All the carryover get fed back in, and then on the next run, you now have more promoters, right? And this is a lot like how our bodies works, right? If you are standing in a zoo, right, and the next thing you know, you turn around and you see a jaguar that got loose from its cage, all of a sudden your body's going to react by creating a bunch of, hopefully, adrenaline or some fear response or something like that. That is your promoters being activated and creating proteins, aka hormones, that will bind to receptors that then like get you to respond a certain way. And this is what this is inspired by. And the hope is with this design, as the organisms or whatever you want to classify them as learn over time, they will learn relations with activating and deactivating promoters to create proteins that then bind to receptors that then activate inputs or outputs. This has probably been really technical, and I'm sorry, but this is really exciting and fun for me. Let's see. There's a bunch of. I'm gonna pause here before I continue on. Message. I thought about all this wanting to create an evolutionary simulator. You're getting ahead of me, Mr. K. You're getting ahead of me. What breakthrough is he going to make with AI? I'm not gonna lie, I kind of clickbaited you a bit. I don't know if this is breakthrough at all. It's just fun research, but we'll see what happens. Right now, I'm just messing with toy examples. I eventually would like to expand it out to bigger examples, but I'll show you the toy example in just 1 second. Let me get caught up on chat. What's cooking, Jabrillium? What's up, Agile Flight? Shouts to you. Can you clarify the goal of such a design? Fire, fire, fire. We love the techniques. Shouts to Outer Cloud. Just got here. What? Were we changing the game? Are we changing it? We're trying to. We're having fun. hopefully in the process of having fun, we'll discover something, but maybe not. Who knows? And there's so many papers out. Like I can't be bothered to read every single machine learning paper that comes out. Like maybe someone's already discovered this or something like this. I don't know. I'm having fun, and what I'm going to show you, it surprisingly works, which I don't know how, but I'll show you in a second. Maybe disabling playback controls on a technical stream wasn't the best idea. Listen, I know I prefer it. Just real quick, I disabled DVR, and the reason why I do that is because sometimes people come to the stream and then somehow they don't know they're like 30 minutes behind, and so they're like asking questions from 30 minutes ago, and I get confused, and it's just a mess. If you want to see the whole stream, it's gonna be a short stream today. You can watch it after this stream ends. Wait, someone's gonna ask. Someone asked a question. I forgot. I don't know. Let's move on. DNA. So what you're saying is your neural network will be built differently. Yes, yes. Actually, Suspicion Crow, there is no weights whatsoever. There is no weights whatsoever in this network, or I don't even know what to call it, this architecture. I'll show you what the data looks like real quick. I'm gonna create a population, and then this is like the data, right? This is all the data, and it's encoded using the four nucleotides, the four base nucleotides of biology. Telomere here is C. I'm not going to get into all the details, but telomere, inspired by biology, is a C. Stop signals, start codons. This is transcribed RNA, mRNA. And then you have the start receptor nucleotide, stop receptor nucleotide. You have the mRNA output receptors, and then the promoter binds. And all of this data can be mutated. That's how you obviously land on different solutions. And this right here is the template strand. It's just encoded into the into a hexadecimal. But yeah, so this is essentially like the weights of this architecture. Like how the human brain works, meat networks. Since AI is inspired by how neurons work in the brain, even though it isn't completely networking meetups. This is pretty cool, and the length at which you associate it to biology. Mr. Kid, I'm listen, I'm not even gassing it. I was just doing this because I thought it was a fun idea to explore, but the fact that it actually can converge blew my mind away. It blew my mind away. And it's really sad. I can't really get into all the technical details today. Wait for the video that release on this. It'll get into more of the details because we'll be here for like 2 hours just trying to go into the nitty gritty of it all. But yeah, here's just like a quick little overview. You can see some of the different organisms. These have like slightly different starting conditions. And yeah, I'm gonna get the simulation run real quick so I can just kind of show you. I'm pretty sure there's a lot of stuff that I'm missing, but I'm gonna run the sim and we'll get that going. So when the sim runs, I have it set up so that we can see graphs. It'll kind of show us the performance. But before of all that, I have to kind of walk you through what the metrics are and all that stuff. So give it a second here to generate the first generation, and I'll walk you through that. Do I have an error? No, it's still running. There we go. Why is this red? That's I don't like that. Why is it red? Red is a bad color. Anyways, it generated, so I can show you. So here we have the first generation. And what you're looking at is it's 100 organisms. That is the cap for the organisms for each generation. And they are tasked with getting as far away as possible from the center, right? Really simple goal that I gave them. Let me see. See, my I haven't did the DVR on my actual like studio from the creator site, and it just desyncs. I think I can refresh this. It's just frustrating. Hold on. Sorry, I'm getting distracted. Cool. All right. Cool. DVR is off. Now I can look at and know that I'm okay. Cool. So what I was saying. So this is 100. This is 100 organisms. They all are randomly instantiated with random DNA. and they all take an attempt to get as far away as possible from the center. Really simple toy example, right? Nothing too serious. Just need to make sure that it works. And we can extract this out later with even more complex problems. Someone is revving their engine. Uh, and so it's really simple. You can look at this and you can immediately tell what the most optimal solution are, right? It's one of four. You either get to this top corner, this top corner, that top corner, that top corner. Those are the four most optimal solutions for this environment. Simple enough, right? Simple enough. I'll take a pause here before we continue. Check the comments. It's pretty cool. If you have the time, you should check out Michael Levin. Definitely, if you're interested in Michael, biomimicry, I'll check him out. Post it on the Discord, Hakuna, so I can remember because I already forgot. Is this your own simulation? Yes, I did this all from scratch, baby. Little Python and a little elbow grease. What do you say is data as a dictionary? Wait, what? When you say the data is that a dictionary? I'm not sure what you mean. I mean, data can be sliced in many different ways, but I'm not sure what I was referencing there. It needs to be considered a drug. Red because of Git plugin. You could even go further by making each molecule self-optimizing. Add real-time feedback and loops. Yeah, I mean, look, this is not perfect by any means. There's so many different areas in which I can optimize it, but it's good enough to show off at this moment. So is this possibly mathematically equivalent to an artificial neural network? That's a good question. I don't know. I don't know. There has to be more tests and whatnot to really decipher the differences. This could even be like pointless. All this could be pointless. Like I'm not gonna sit here and pretend like I did this world breaking breakthrough or anything like that. I have no idea. It's just fun and it surprisingly is converging. So I'm gonna keep going. This kind of reminds me of Sebastian League's coding adventure series where he made rabbits breed and create their own colony. Shouts to Sebastian League. I love his content. If you added weights with deterioration to those paths, would that literally be like forming memories for the AI, giving them unique personalities to solving problems? If you added weights with deterioration to those paths, I mean that's a different algorithm that you're talking about. The hope is that like this algorithm isn't just confined to this toy example that I'm giving. But let's move on. Let's move on. So I have data that we can look at, right? So here is the score averages over generations. Here's the score average, and then here is the generation. We're currently on generation 11. They are doing the best they can to evolve. And I have a little secret to share with you all. So I am only really doing this stream because I'm looking for a bug at this moment. There's a bug where they like over time, it takes usually about 100 generations. They'll go up and up and up over time. And then around like 150, 200, they do a quick spike, like shoof, they just shoot up super quick. And what I have found is that they find a really optimal strategy that can be found randomly on one of the starting random configurations because it just goes straight to the wall, just straight. Like the organism's configuration is set up to only go move forward, and so it just slams against the wall, and its score outperforms every other creature in the pool, and then every other creature then just copies their technique, and then they get stuck there. And I think I have a solution for this, but before I implement the solution, I want to first see it because I added another graph, which is speciation over time. This just shows like all the different species that are attempting and then how prominent they are per generation. And if I get to see that when that bug occurs, if there's one species that just completely dominates this, this one just popped up, completely dominates the gene pool, then my intuition will be confirmed, and then I can, in confidence, add fix the bug. Um, yeah, what's going on here? Damn, those videos around the screen is trippy sometimes. You. Oh man, I must be high right now. Are you saying that the problem is inbreeding? Kinda. I think the problem is deeper than inbreeding. The problem specifically is that there's not speciation. I don't I'm doing I have a way to cluster species at the moment, but I'm not scaling the scores per species. So whatever score the individual gets, it's that's the score they get, no matter what species they are. So what happens is, say that you have like species A that does the strategy I just told you, right? It just goes from the beginning, just forward all the way to the wall. Its score is going to be what 10, 20, 30x higher than the average. And so when it comes time to mating for the next generation, they're going to get far more chances to mate than any other organism in the pool. And over like 2 or 3 generations, like it's going to completely wipe out every other species. That's at least my intuition. Once again, once I see that happen, I can check this graph and get confirmation. Uh, and then the solution then is to add speciation, where your score is going to be scaled by the number of organisms in your species to kind of like give opportunity for other species to look for other um, solutions. How do you calculate species? It's very complicated. It's very complicated, but I'll give you the high level. Uh, the speciation is not binary in this algorithm, in this architecture. It you belong to many different species at a certain percentage, right? You have a certain, like, I think it's called like a similarity score or something like that, where you just compare your DNA to the DNA of. Oh my gosh, it's very complicated. Long story short, we start off with no species, right? And then there's a check to see, give me the species list, and here's my DNA. Does my DNA match any of the species that is in the species list, right? If the species list is empty, then it says, no, it does not. Okay, then here's my DNA, make that a species, right? And so now we have one species, we have one DNA in the species list, right? Then the next organism comes and he says, here's my DNA, compare it to all of the DNA in the species list, so on and so forth, right? So then if it's close enough, then it says, okay, then I'm of that species. If it's not, then it adds a new one. Eventually, over time, you will get a cluster of similar enough species, and then they all. And again, it's not binary, so it's not like I hate doing. I hate bias. So anytime I have the opportunity to remove bias, I will. And so instead of saying like if you're over 50% similarity, then you are of that species. It's no, you are this percentage related to this species, or this percentage related to this species, this percentage related to that species. Um, yeah, I hope that answers the question. Isn't that normal? Before I also have been curious to know, like, how many of these can I run on this computer? Let me just do that real quick. Let's see if I can do another simulation, like a duel. If my computer will blow up or not. So I'm gonna do test 4, and let's run test 4 in 2 different windows. Will it work? Look like it's working. What's the limit? Can I run 10 of them? Surely my RAM or something. No, I removed all the RAM dependency. Well, obviously it's using some RAM, but storage is more. I wonder. If this generates the first generation, I'm gonna run the second one. I mean the third one. Because why not? It did. All right, I'm gonna try and see if we can do like five different runs in parallel. Why not? Oh wait, I think my computer's slowing down a little bit. All right, let's do test 6. This is perfect, yo. All right, I'm just gonna do 4 of them. Nah, I ain't gonna bitch out. I'm gonna do 5 of them. I ain't gonna bitch out. Watch my computer just reset on me. I mean, it's a pretty simple task. It shouldn't. My computer should be able to handle it. All right, we got 5 different pools running. One of them should show the bug eventually. Okay, let's get back to the comments. Oh, cool. I tuned in late, so I'm not sure what the goal is. Title says AI. How many of these can you run? Haha. Jim. Jim. So the goal is I'm currently fishing. I created a or I'm working on exploring like different AI approaches, and one of them is instead of being inspired by the uh, brain, this is inspired by microbiology, like the core idea of microbiology, the 4 different nucleotides, and yeah, we're seeing if this works. But at this moment, what I'm fishing for is I'm trying to see the bug. There's a bug that I have where they just suddenly um, converge onto one solution and completely ruin the run. I'm looking for generations. No, no, no. I don't care. This one's still doing pretty bad. On generation 35. Let's check out test 4. Test 4 is generations. This one just started, okay? So that means the rest are gonna be still. Yeah, okay, we'll give them a little time to try and figure it out. But yeah, let's see. Single threaded. Ha. Please don't chastise me on multi-threading right now. It's a pleasure to be here and chat with you. Shouts to Jack93885. Not sure what's up with the guitar and music, but I'm into it. Bitrate dropping. Oh, is that true? Is my bitrate dropping for real? Is this how some bugs? How about some bugs at random have defective DNA that hinders and or optimizes their performances? How about some bugs at random? I don't know what you mean by that, Dan. However, when they mate, they will do either or. They'll either be hindered or optimized. I'm using a genetic algorithm, so just by nature of the genetic algorithm, like that's gonna occur naturally. I think this would be an issue. I think it's wait. I would think it's an issue with the extreme simplified task. Would it help if there were obstacles or mating success depending on vicinity or compatible species? So Macabout, I mean, you're not wrong. You're not wrong, but this is a stepping stone. Like I have to first prove out that this works before I can go to even more harder things. Because if I just go straight to the hard thing and it doesn't work, then it's harder for me to understand if like there's something wrong with my approach or if the problem is just too hard, right? So to keep it nice and simple and it just first prove that it works gives me the confidence to be like, okay, now we can do an even harder problem. Like we can simulate this AI trying to play Minecraft or something like that. You know what I mean? Score average is lowering fast. Yeah, just give them some time. About generation 100, they'll usually find their footing. Sometimes they oh, it looks like they might be finding footing now. Maybe spoke too soon. Sometimes they find it very early. Sometimes they never find it. But usually about 100 where I start to get worried if it'll never converge. Uh, so keeping so in keeping with the metaphor, you would need more mutation to decluster. You would need more mutation to decluster. Not sure what you mean by this, but yes, yeah, you need more mutation because the problem that I was trying to solve is that like if you cluster them with binary tags, right? Like you explicitly belong to this or you explicitly belong to this, even though you share like 33% of your DNA with another one, you explicitly belong to this one. The problem is that like if you have one organism that mutates into another its own classified organism, right, and does really well, well, guess what? If it's the only organism, it can't mate with any other organism. Like it just is incompatible. And so it's actually inspired by real biology. There are transitional periods between when species go from one species to another species where they can no longer mate. There's a transitional period where like sometimes they can mate, sometimes they can, until like the genetic drift is too far. So I was trying to simulate that, and I believe that it's gonna bear some good fruit in the long term. Do you have a low mutation rate? Actually, I think I do. Yeah, I think I do. That again, I hate bias, but I the mutation rate is low at the moment. I think that slow and steady is a good starting foundation, and then in the future you can jump in there and try and like play with the mutation rate and see if you know. Ideally, I would love to have the mutation rate set by the organisms or the environment. Ideally, but again, it's still pretty early. I haven't got there yet. Yeah, perhaps more mutation by volatility or chance for extreme mutations will prevent convergence to one species. How many minutes is a generation? They vary, and the more data, like let's see, this one is most of it comes from the simulating all the frames. They're about 35 seconds per generation. I think the furthest from the center that gains points for this. Yeah, yeah, that's correct. The furthest from the center, the furthest you are from the center, the higher your score is. Correct. Which again is why these four corners is the highest, is the most optimal that you can get in any run. And it gets exciting when they once they start to find their groove and figure it out. But sometimes it takes a few minutes. Sometimes. Um, how do you determine that? Is a good question. How do you determine that transitional state? Isn't it arbitrary when they would become incompatible? Isn't it arbitrary? Yeah. So Jonas, this is not set by the algorithm whatsoever. It's either they have enough DNA to create viable offspring or they don't, right? And it's very possible that there are two organisms that may have an offspring that is infertile, that can't have offspring at all. That's very possible. Um, Unlikely, but it is possible. Determining what when a species can no longer crossbreed will be interesting to hear how you solve it. Uh, I don't think I'm explaining this well enough. Let me see if I can provide some visuals, perhaps. Maybe the genetic algorithm script. Let me see. Maybe this will do. Man, this is so technical. uh, okay, I'll try my best. Okay, so when we take two parents, right? Here's the function that controls offspring. We take two parents, parent one, parent two. We roll a random dice, and then we simply just ask, is the dice lower than their similarity score between these two organisms, right? And what is considered for the similarity score is we take the entire nucleotide, we convert it from the hex compression back to the nucleotide, so we have the genome, and then we turn the genome into chromosomes, right? This is very foundational to how animals work in our actual animal kingdom, right? Now we have our chromosomes from parent A and parent B, right? Oh man, this is technical as hell. We need to get the count for both chromosomes. Very important. Very, very important. If you ever know things like Down syndrome, etc., when you hear people say I have an extra chromosome, this is what's at play. Chromosome matching is very important when it comes to creating offspring. Um, we get the count, and then we compare the two. Wait, no, I'm sorry. We get how many comparable chromosomes we have, right? Which is the minimum between the count of the two, right? And then we have the maximum. We need to get the maximum so that we know how many total between the two. And then we can get the genome compatibility score, which is simply just the count divided by the max. Count of, sorry, I wrote this a while back. What am I doing? If the count matches, this will indicate how close the organ is. Compute the absolute value of the count delta. Yeah, so we take the count delta, take the absolute value of the count delta, then we put that over the max chromosome, and then we do 1 minus that to get the compatibility score. So that means that if the chromosome counts are the exact same, the compatibility score for the genome is going to be 1. It's going to be an exact match, right? An exact match. If they have completely different count, it'll never be 0. Like it'll always be 1 over, at least 1 over something, right? Wait, is that true? Give me 1 second. Let me just hold on. Give me 1 second. Let's just assume that they both are 10. 10 minus 10 is going to be 0 over 0, so it's 1. Yeah, exact match. And then if it's 5 over 10, it's going to be 5 over 10 minus 5, half, 0.5. Right. But if it's 1, that's the minimum chromosomes you can have is 1. So 1 divided by, let's just say 10, it's going to be 9. I'm sorry, 1 minus 10 is 9 over 10 is going to be 0.9. 1 minus 0.9 is 0.1. Yeah, so then I guess the lowest it can be is really low, but it can't be 0, right? Anyways, moving on. You take this compatibility score, save it for later. Now you have to compare the actual chromosomes, each individual chromosomes themselves, right? Because chromosome alignment is really important when it comes to actual biology. And it's basically the same thing. You take the nucleotide count of a chromosome for each of them that you're comparing, and you just align them perfectly, right? This may not be exactly how they do it. There might be like markers or something where you can shuffle them around and find the right ones, whatever, but we're not simulating it that deep. We just go straight down the list. You take the max, you need a reference to the max nucleotides. And so then you get the chromosome compatibility score, which is very similar. You get the count of A and B, you get the delta, and you put that over the max nucleotides, and you subtract that from 1, right? If they are the exact count, if you have 10 and 10, it's going to be 0 over 10, right? And then 1 minus 0 is 1, right? Exact match, perfect score, right? And then you append all of them, whatever the count of chromosomes may be, and then you take the average of the total score for all the different chromosomes, and that'll give you the average chromosome score. And then what you finally need to do is you need to take that average score and you need to scale it by the genome compatibility score. And that gives you the final similarity score, right? So then we can go back to our compatibility. Remember the dice roll. If the dice roll is greater than the similarity score, then they're viable. If it's lower than, if it's greater than, they're not viable. If it's lower than, they are viable. Which is why if it's a perfect match, if it's a 1, it will always be viable. And if they're very far apart, there's still a tiny chance. But and as the genome gets more and more complex, it gets harder and harder, closer to 0, but never fully 0. That might be a flaw, but I think that it's good enough. Yeah, I think it's good enough. Hopefully that answered your question. I don't know. I just on that ramble. Thanks for giving me the space to ramble about some deep algorithm stuff. Let's see how our generations are doing. Okay, this one's doing a little better in our second. This one is doing not too hot. This is 1, 2, 3. We have a couple more to check on. Let's check on test 6 and 7. See how they're doing. Okay, looks like this one is doing something. Trying to at least. Oh, I clicked the wrong thing. I'm starting to get confused. All these tabs open. All right. Okay, so it looks like our first one is still struggling to figure out a solution. Okay, our second one here looks like it's doing something. There's a little uptrend there. Third one is not doing too hot. Fourth one is still trying. Last one's still trying. Let's check in on this one. I think this is test 5 is the name. Let's see how they're doing. Oops, I didn't mean to click that. All right. All right, so it looks like this Discord colored organism has figured something out. Okay, we got the little teal one here. Green's doing pretty good. This red came out of nowhere. Okay. I promise you it gets better. We just have to we just have to give it a little time. But I promise you it gets better. It gets a lot more exciting. I'm gonna get caught up on comments, or at least I'm gonna try to. Is mutation is a mutation always the same size? If not, you could fit the size of the mutation to a distribution curve and tune that to make sure there's the right amount of mutation. I'm skeptical to believe that there is a such thing as a right amount of mutation. I'm very skeptical about that. Um, I do want to remove the bias of the mutation. I have some ideas, but I don't have the brain capacity to think about it at this moment. Have you ever looked at elitism with random individuals who had diversity? You're trying to make unsupervised GANs. No, not no. I'm not sure if this would even be able to generate images and stuff. I'm not sure if this algorithm could do that, but maybe in the future we can try and explore that. Any recommendation to start learning to build neural networks? Just start building them. To be honest, just right now, open Python and just start building them. You'll get stuck, and then wherever you get stuck, type that in Google and apply that. You'll get stuck again. Type into Google and just keep going. Are you introducing predator and prey species in this? Lion, that is the perfect question. So another part of the stream, the reason why I want to do the stream is because I wanted to fish. What should the next example be to demonstrate that this algorithm works? Uh, I'm pretty tired of watching these organisms optimize to try and get to a corner. And I promise you they do it. I will show it to you. I promise. Oh, we got some activity. And oh, this is test 4. Wait, I looked at the wrong one. Test 4? What is this? Test 3. Oh, we looked at the wrong one. Test 4 is doing something. Test 6 still struggling. Test 7 still struggling. This is test 5. Why are you here? I'll put you in order. Let's make sure test 7 is the last one. I think so. Yeah. Okay, so test 4 is our one that's doing something. So let's go look at test 4 actually. See what they're doing. Okay, so we see there's definitely a prominent species here. It's the magenta. And it looks like there's like a carrot orange at second. Or maybe the teal. But as you can see, they're all collectively like spreading, getting further away from the center collectively, which drives up that average score, which is good to see. Generation 4 is doing God's work. Let's look at the speciation for Generation 4. I'm sorry for test 4. Okay. It looks like FOF is dying off. Looks like I can't pronounce that. Quirk is slowly dying off. Looks like I think this is Sekijo. Seen better days. Oh, this one right here. This is Zibby. Zibby is about to be rip. They aren't doing too hot. Just like I'm looking Roko love it. Is this just species evolution, or are you also coding a whole ecosystem that evolves? At the moment, no ecosystem. I would like to add that, uh, so that we have something more exciting to watch. But at this moment, this is just a toy example to prove that it works. And again, it's their objective is to try and reach one of the four corners as the most optimal solution. But I 100% would love to get to the point where we add like an actual like emergent behavior unfolding on screen. Looping through to compare looks inefficient. Put everything in a NumPy array. Eduardo, I love you, but I'm not at the point of optimization yet. I gotta make sure it works. I'm not gonna waste time yet. I gotta make sure it works first. Great explanation as a PhD. Yes, listen to me. All of my biology takes are correct. You can use gradient descent. You can use gradients to supervise mutations, no? Instead of only relying on chance. Am I getting what you're doing? I'm not sure what application you are trying to use gradients here. If you can go into more details, maybe we can get on the same page, but I'm not entirely sure what application you mean there. To supervise mutations. You might be right. I don't think I understand enough though. Okay, where are we? This is test 4. Right. How are they doing? Okay, they're still holding strong. Pretty good. How are we doing on 3? 3 is getting worse. Oh my god. 3 is doing terrible. What is happening with 3? How is that the dominant species? I've never seen it get this bad before. Like so consistently. Interesting. We'll check back on 3. Let's see how 5 is doing. Okay. 5 is above average. Red above the red line is above average. So they're doing above average at the moment. We'll check back on them. And then 6 is still doing pretty bad. Generation 30. Generation 30. And it looks like they're still doing bad. Okay. I think our best soldier is 4. I think they're going to beat the max score pretty soon here. 3 is still struggling. And 3 is drowning, yo. It's on 60 and still drowning. Uh, Backtracking. Yeah, no, so I'm using a genetic algorithm for the evolution of this. Uh, Doing a gradient on the mutation, that's not obvious to me. Maybe you can explain how that works. It might be a good idea. I'm not too sure. How does DNA influence their movement? Mac about. Sure. Let's just go over that really quick. Where is? Did I close it? I closed it like an asshole. So real quick. So how the would you ask? How does DNA influence their movements? Okay. So it all really stems from this promoter activation. And this is based on real biology. So the way our body works is we have DNA, right? That we have like little machines in our body that reads our DNA, it converts it into mRNA, which then the mRNA is converted to proteins. The proteins are then treated as hormones and machines and all different types of stuff, right? So being inspired by that process, your DNA is a string of genetic information, and essentially they are searching. Every organism is searching for like the optimal DNA to like protein activation or protein production rather. And so how it works is the input is immediately binded to external receptors, and there's more than 3 inputs. There's 4, I believe, which is simply just like distance to the left edge, distance to the top edge, bottom edge, and right edge. and they immediately bind to external receptors, which then will maybe, possibly, potentially activate promoters depending on their DNA, right? And the promoters just bind on a section of the DNA, and then will just comb through the DNA till it hits a stop signal, and then it will extract that as a mRNA. The mRNA then gets turned into protein, and the proteins then bind to the internal receptors. Now, if the protein that is created binds to an output receptor, then the output will be activated for that frame, for that simulation frame, right? If not, then it won't be. And there are four outputs. There's three outputs. There's turn left, turn right, move forward. Um, and then sometimes some protein activations can bind to other internal receptors, which uh, their only goal, the only objective is to create more proteins. I'm sorry, is to activate more promoters. So if that does happen here on the last layer, then that carryover is just fed back into the next promoter activation. So the idea is that if you have like a good setup, let's just again use the scenario that I presented at the start of the stream. You have an organism that is like at the zoo, right? It turns around and sees a lion that's loose. It should be in its cage, but it's right there, loose, staring at you, salivating, about to eat you. The idea is that that will be represented somehow in these inputs, and that input will then trigger one of these receptors to turn on promoter activation, which then create the correct proteins that will then go and bind to the right outputs, right? Maybe the output is like run away, or maybe the output is like call the police, or maybe the output is like cry to your mom or something like that. That's the hope. So like the organisms are searching for that correct configuration, and they are searching for that through means of the genetic algorithm. Thanks for coming to my TED Talk. Boy, this reminds me of Carly Zlolny Feher used a genetic algorithm to recreate the Mona Lisa from colored triangles. Makes sense. Dude, people sleep. Yo, let me go. Yo, hold up. Let me go on a genetic algorithm rant real quick, okay? I think genetic algorithms are the greatest, like, means of optimizing algorithms that there is. The greatest. I don't think there's anything greater. Fuck your gradient descent. Fuck your optimizers, this and that. Fuck all of that, dude. Why do I say this? I think that everything inherently needs to be rooted in biology. And like the closer you can get to like the base biology, the better it is. And I remember back when I was really excited about doing artificial intelligence, and I was reading a lot of papers, and I was doing a lot of practice, and blah blah blah. I was in the community. One of the biggest arguments was that genetic algorithms were too slow. And yeah, that is true. That is true. But that doesn't mean it's bad, right? Would you say that all of humanity is bad, right? Because we're the result of hundreds of thousands of years of slow evolution. Um, I think we just need to like chill a little bit. We need to relax on like, the whole push of capitalism. Just like, hey, look, slow down. We're going to use this really slow algorithm. It's slow, but it's very, very, very meticulous. So what's the word I'm looking for? It's like very, very thorough. Thorough is what the word I'm looking for. Shouts to genetic algorithms. All right. Thanks for the answer. It makes sense now. I agree, but the problem with your approach is that you rely on a single central plan. The beauty of a genetic algorithm is that each cell has localized intelligence. Wait, what? I agree, but the problem is their approach to rely on a single central plan? No, well, yes, Hakuna, yes, you're not wrong, but you don't have an issue with the algorithm. You have an issue with the reward structure, right? I'm rewarding them to get as far away as possible from the center. And technically speaking, they're not really doing any collaboration. So there is no like central plan. It's just they're all rewarded to do something really dumb. But if we change the environment a bit and rewarded them with like, hey, survive as long as possible, they're gonna create how you say localized intelligence. Are you gonna share the code? Yeah, I am planning to release the code. Not yet. I want to get a little more polished, and I'll release it. It's a question of being feasible, not fast or slow. Well, you say that, but if you go back to some of the early AI days, everyone was huge on that. We needed to go fast. We need to be done in a year so that we can get this investor money. Da, 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 da. Which, to be fair, a lot of money was made. So it is what it is. Let's check back on our generations. Let's see how they're doing. Generation 3 is still struggling. How's 4 doing? Okay, 4. I wish 4 was doing a little better. 5 went the wrong way. Okay, 6 is doing terrible. Interesting. Again, it's usually around generation 100 where I start to freak out if they are never going to converge or not, or at least converge too slow than I would like to see for this test. Uh, Not quite there yet. But yeah, maybe I can change the mutation rate on a run, a single run. I think I can do that and just see how it changes. That's going to be in genetic algorithm, I think. Mutate. No, I don't use this function at all. Do I? I don't think I use this function at all. I think it's legacy. This is the one right here. Try to mutate organisms. So yeah, so it currently has a 1% mutation rate. It's fixed. It's biased. I know. I hate it too. Okay, I'm gonna change it when I get there. But maybe I can increase this to a 10%. Let's just try 10% and just see what happens. 10x. I'm gonna run it on one more. Generation 8. Our test 8 is gonna be our test. Our mutate. I'm gonna call it mutate. So it's yeah. All right. Let's see how this changes. And then now that that's ran, I'm going to turn it back to 1% because I will forget that I changed that in the future, and it will cause me 3 days trying to figure out why everything is not working like it used to. Okay, cool. We got that running. Hopefully my bit rate still is good. Thanks, Heart. I think the reason evolution works in nature is because it's statistically inevitable. In a human constructed model for a very specific problem, backpropagation using a calculus derivative algorithm is GRIAS. Great, it's great. I think backpropagation for sure has a lot of use. Like following any gradient, I think like gradient optimized solutions I think they're great. However, I think they have their limits because in order for you to do a gradient optimized solution in the first place, you have to introduce so much bias, and that's the part that like I find the gripe. It's like I don't want to have to define all these parameters. Like I want to create a system in which it optimizes for these parameters itself, and just through running the simulation, it will eventually converge on whatever the most optimal solution is. I like the reward model. I realized that if you reverse your thinking and treat users as the AI, you can map actions into strength values and have attribution on them. That's likely how TikTok. Time for a trim. Talking about me old beard here. Talking about me old beard here. I was adapting that into an app for a startup I was working at, and got some game devs excited when I talked about it as an approach. Still a good mechanism, I think. I'm not gonna lie, I'm not quite sure what you're getting at there, Evil Spy Boy. What I'm trying to say is you don't utilize the algorithm. Your genetic algorithm finds a good enough solution and stops exploring. That being said, I think you've already proven what you want here and should just continue. All problems you have now will just be solved later on. I don't agree. I don't agree with the stop exploring part. I think it'll continue to explore. I think that they'll hit plateaus, and the plateaus may last longer than I might want them to, but just from all the runs that I've done, they eventually will find some general solution. Um, but I say that all with, I do think there are ways to improve, to assist them with not getting stuck in plateaus, one of which I think is speciation. Um, but I don't think I've ever seen them perform this bad. This is a good healthy. This is a good healthy. This one's going to converge. Test 4 is going to converge, but all the other ones are like, they have stage fright. I don't know what's going on right now. And this could even be a result of not having a good speciation algorithm in the sim too. You have different rewards for different behaviors that makes a user profile that shows them what they like slash do. Then because human, you have to you have attrition on the rewards. Yeah, I think that's I think you're describing like how most social media works. I think that's what's going on there. Yeah, this is healthy. Test 4 is definitely going to converge for sure. Look at that uptrend. Look at that uptrend. Test 3, I still believe in test 3. I believe they can I believe they can pull through. Test 5, I believe in test 5 too. They're just, they're growers. They're not showers. Test 6. Test 7 looks a little weird. Let's check out our mutate one. Let's check out our mutate cohort. See how they're doing. I went too far. This is generations. Okay, we only have a couple of data points, but it looks like it's not as low as the other ones. At least what is this, generation 3? Generation 3? It's negligible, I guess. Yeah, we'll give that some time to grow. This is my first time running this many generations simultaneously. This is healthy though. With test 4 is the excuse me, is the one. Who's gonna be second place? Someone has to pull through. There's too many runs for only one of them to be viable by generation 100. Let's check in on test 4. Well, first let's check out the species, see how they're doing. So it looks like Dude Q is dying off. Ooh, these are like the same color. I don't even know. But pink here, the Gira is going really strong. And then it's Gira, and then it's Vavubi. I think Vavubi is this one right here. And then it's, I can't say that, Sivuvui. Sivuvui is this next one up, I think. No, yeah, this next one up. No, that's gonna be this one. This one is Datab. Oh wow, Sivuvui just went up by a lot on this last one. How are we looking on the graph? Okay, okay. Let's check in, see how they're doing. Looking healthy. So that's Sivuvui right there. I don't remember what the pink one's called again. I've seen better, but not bad. I ain't hating. I ain't hating. It's premature convergence that kills progress. Your population needs more exploration before settling into a solution. They stop adapting too fast. All right. Well, I'm supposed to be home for lunch. I mean, for dinner. Oops, I think I got a missed call. I'm gonna get in trouble. My fiance's gonna kill me. Quantum. Is the population large enough? That's a great question. Bob, BCBR. That's a great question. I don't know how to answer that. Yeah, that's another dimension to explore, right? Mutation rate is one of them. Adding speciation is another one of them. The population size is another one of them. Gira Pink. It's still looking healthy. It's still looking healthy. We'll give them a little more time. Let's check in on some other. My God. 3. Will you stop embarrassing me on this live stream right now? How long have I been going? An hour, 10 minutes. Okay. Oh, look at that. Midnight hour on generation 51 or 2. We got some good progress above average, way above average. Pretty good. Please hold this. Test 5. You can do it. You can do it. We'll come back to you. Generation 6 doing poorly. Generation 7 doing poorly. And our mutate. Oh, that's a pretty healthy curve. I'm not gonna lie. Excuse me. Yo, who was it that was suggesting a higher mutation rate? I think you might be onto something. That's a pretty healthy curve. That is a pretty healthy curve, huh? A good amount of exploration, huh? Okay. What program is the program trying to solve? Janik. So really simple. All they're trying to do is get as far away from the center as possible. That's it. Really simple toy example. And the most optimal solutions are corner 1, corner 2, corner 3, corner 4. Simple as that. Will they do it? I have high faith. I've seen some incredible stuff over the past couple of days. But sometimes they take a little while. This is still a healthy curve. I think that test 4 is going to get it eventually. I'm not sure if test 5 is about to rebound or not. Let's see. Oh, they went back down. Never mind. Okay, looks like they're a little above average. Are they going to dig out of the hole? Test 6. Let's see. Test 7. Okay, test 7 started to come out the hole. It's like 50 is around 50 seems to be where a lot of these are trying to rebound. But our old reliable test 4 has been out of the mud since generation like 25, dude. Early bloomer. Test 3 is just pathetic, dude. Just pathetic. Generation 80, no signs of life. The lights are on, but no one is home. This is an interesting healthy curve with the mutation rate of 10%. We'll see how it continues to grow, but this is pretty healthy. Very interesting. Okay, I'm not gonna lie. I don't have much time. I need to be home for dinner. But this is so much fun. This is the stuff I dream about. I dream about like just watching dumbass algorithms like this go. Like, also, I don't want the stream to go on too long, other than the VOD becomes a little cumbersome to watch. I think I'll be here for like another 7 minutes, and then I'm out. I'll be back another day. Come on, I had so much faith in you, test 5. Show us above average in the next one, please. Above average, please, please, please. Come on, come on. Come on. Few species dominate too early. Other than that, fun stuff. Come on, come on, come on. Come on. How do I scroll this? Oh. There we go. That's 5. What are you doing? Show us something. Show us something. Oh, boo. Test 6 is trying something. They're trying something out, but I don't have high hopes. Test 7, they're making the attempt, but I don't have high hopes. Mutate. Oh my god. Oh my god. Mutate. The 10% mutation rate is hitting a little different right now. Let's check in with Mutate. Let's see what they're doing. Let's see what they're doing. Okay. There's a clear dominating organism. It's the little purple ones. But I don't think the score comes from them. It has to come from this one. It has to come from this one. From this organism, I mean this species is putting in work for the entire pool. Okay, there's a couple of the purple ones that are doing some work. Okay, so these two are putting in a good amount of work. Let's get familiar with the names. Let's see. We got, oh my God. Quickazimk. And the other one I think it has to be this one. Sutakau and Quickazim. Oh my God. What is going on with the mutation pool? Holy. Let's see. Let's check back in. They're figuring something out. Oh, there we go. So Sutakau definitely is taking over the population. Sutakau is taking over. Maybe the bug will happen now. Maybe I'll be able to experience it before I get off the stream. That'll be great. If Sutakau completely takes over the pool and I get to see it on graph, I don't know exactly how to fix it. It looks like it's about to happen because there's a lot less whatever they're called, and a lot more Sutakaus. And I expect in like 2 generations, it's gonna be like primarily Sutakaus. This is exciting. Okay, let's mark this graph. We found one. Wait, before we do, add a little suspense. Let's go check on all the other pools. Okay, Tesla, you're a disgrace. I'm proud. I mean, I'm disgraced. I am disappointed. I am. What's the word I'm looking for? I'm like, I'm lost at words. Like, how dare you get on my stream and perform this poorly? We're gonna check on 4 last. 5 is trying. Test 5 is trying. Test 6. Test 7. All right. How we doing 4? Come on. I need at least 2 to make me look good. Come on. It's still healthy. It's slow and steady, but it's still healthy. Kind of stagnating a little bit here, but it's still healthy overall. It's still healthy. All right. Back to the real big timer. Mutate. Oh my God. We still don't have an update yet, though. We're looking for that generation 14. Just join the stream. What is the experiment with? Seems like an evolutionary algorithm. Correct. You are correct. This is an evolutionary algorithm. We're using specifically the genetic algorithm. I am exploring a new homebrew. Wait. I think we have found the bug. I think this is it. The bug usually stops about 120. But because this is a different organism, I don't think it's going to stop at 120. But still yet, I think it should still demonstrate the point. Yep. Look at all the Sutakaus. Wait, let me just confirm I'm saying that right. Wait, Sutakau? Oh, Sutakau's up top. I thought Sutakau was at the bottom. Okay, Sutakau. But it looks like there's still a good distribution. It's not completely taken over. But there's definitely some Sutakau dominance happening. But what can I say? Look, they definitely have a good solution towards the task they were handed. They're exploring. They're getting closer to the 4 optimal edges. They deserve it, you know? Oh, I think I know why. Okay, I understand what's going on here. So there's a couple of confusing things. The graphs. are illustrating the more you fuck around, the more you find out. Zick pranks. Zick pranks. So I think I remember Zick pranks from back in the day. Yo, shout to Zick pranks. What's going on? Uh, wait. So as I was saying, I think I remember. I know what's going on here, right? There's a few things that I didn't properly communicate as to why there's a bit of mismatch between what we see and here and what we see on the graphs. So, like I said, the organisms, they have different percentages of, they belong to different species based on different percentages, right? So all of these Sudical species, even though they are make up, what is that, like, I don't know, an eighth of the population or something like that, and they look like they make up maybe like 80% of the pool, it's because this is, the color here is depicted by the most dominant species they represent. And most organisms probably have a makeup of a bunch of different species, but the most dominant that they have is the Sudical species. So that's what we're seeing here. And honestly, I'm probably going to fix this because I'm a perfectionist. I think one solution to that is, instead of having this be binary, like how many species have that, the speciation, like in their, all these fucking terms, how many organisms have a, even a single percentage of the species in their relationship. I don't know. That I would change it to, oh, okay, so the cow center. I would change it to whatever your percentage is how much score you add to that species for this chart. So if I were to do that, then if, let's just say Sudical makes up like 60% of the species relationship for most organisms, this will be much larger. It'd be much, much, much larger. Oh man, what is this? This is Dadu. Look, Dadu came, did a little well, and then died. R.I.P. to Dadu. Anyways, I think this is reflecting the bug pretty well, though. I need to add speciation to prevent this from happening. This is inexcusable. Because at some point, if we wait long enough, Sudical is going to become 100% of the pool. Well, I guess the most it can be is 90%, because 10% of the pool is new, fresh organisms. But so all this due to a bug, I just jumped in. Yeah. So, well, a bug really is just something that you didn't intend to code, right? So I didn't intend for the organisms to be able to, or the species rather, to just completely dominate all of the species just because their solution is better than the others, right? Because simply put, right, the goal for every organism is to get as far away as possible from the center, right? However, there are, because this is so simple of a goal, we can easily just look at this and figure out what the best solutions are, right? There are four of them. There's get to this top right corner, top left, top right corner, bottom right corner, bottom left corner. There are four equally optimal solutions, right? And the Sudical species might eventually land on getting in the top right, right? It kind of seems like they're heading somewhere on the left side eventually, right? Which is good. That's what we want. However, that isn't the best solution. There might be this green one, right? Might be on the path to figure out that this corner right here, this bottom left corner, is also another optimal one, right? But because I don't have speciation in the algorithm yet, because Sudical just does well, all the Sudicals will breed over and over and over and over and suffocate out all other species eventually, so that they don't even get a chance to try to find other optimal solutions, right? And it's not a big deal when we're talking about this small toy example, but if we were to add this algorithm something more serious, something more extreme, something more complex, that becomes a big problem. Big problem. Check the time. You say you were leaving. You still Macabout, I appreciate you. I'm having fun. I'm sorry. What can I say? I'm having a lot of fun. But I do need to get out of here. Um, uh, what was I saying? Yeah, it becomes a big problem when we try and use this algorithm for more complex problems. So the solution is that we add speciation, and what that is really simply is that uh, let's just assume Suddacal there's 80 Suddacals, right? The total population is 100. Say there's 80 Suddacals, right? If 80 Suddacals all get a score of 100, right? But the average score in the pool is 5, let's just say, right? I'm gonna make the math easy. Let's say the score is 80, right? But the average score is 5, right? Um, that means that when we compare every single organism against every other ones, only the Suddacals are going to be able to mate, right? Just because 80 versus 80 versus 80 versus 80 versus 80 versus 80 versus 5, it's not comparable on a distribution point of view, right? However, if we take into account, like, hey, you are the Suddacal species, you're of the Suddacal species, there's 80 of you, we're going to scale your score by how many are in your species to make it fair for everyone else in the pool. Well, that 80 divided by the 80 Suddacal becomes 1. The new score is 1, right? And let's say that this green one here, let's just say their score is 5, right? And there's 5 in the pool. Well, 5 divided by 5 is 1. So now they're equal playing field. So now Suddacal is going to have to outperform extremely well to be at the top of the food chain. And it just gives more organisms the opportunity to like search for their own solutions without being pressured to copy exactly what the Suddacal is doing just to compete. You know what I'm saying? Suddacal is being outcompeted by purple and green by 10 gen 10. Is that true? Where did you see that? Yeah, the Suddacal, their exploits starting to wane a bit. But also, like, this is all very complicated, right? Because this whole run was only to test the 10% mutation rate, which it looks like did a really, really good job. This is a really healthy and stable line. But again, this is only one run, so I have to run it multiple times to see if that hypothesis remains true. And oh boy, I'm getting a headache. LOL. I'm older. I did work in the chess engine project in my heyday. Shouts chess engine projects are fun. Oh, it looks like they found their peak. Generation was that 16 or 17? They've completely taken over the population. But it seems like green somehow is still surviving somehow. I don't know how. Species. Yeah, and I keep forgetting it's really complex because like Suddacal probably has a good percentage that is compatible with the ZZ. There might even be a fork, to be honest. That's another graph I want to add is what they called them. I forget what they call them. Stacker, Sander graphs or something like that, where you can see like the generations over time. I want to add that so bad. But they might share a lot of DNA so that the Suddacal can mate with the ZZs, keeping them alive or something like that. Um, Rest in peace to the Dadu, man. They didn't stand a chance. Anyways, let's check back in. This is what we're gonna do to end the stream. Let's check back in with all of our other generations. I think I'm probably gonna run them overnight. Uh, and then after we check the back in, we're gonna check back in with our mutate. And then I'm gonna do the comments, and then I'm out. How's that sound? It sounds good. Good. You don't have a choice. That sounds good to you. Okay. Generation 3, disgrace. I hope that you do better when I return in the morning. All right. Oh my God. Test 4 has regressed. Test 4 has regressed. I had so much faith in you. I had so much faith in you. Test 5, still stagnant. Okay. Test 6. Mm-mm. Wow. No, they all sucked ass except for this one, the mutate one, where we found the bug. Okay. I just want to see one more generation, generation 18, just see where it goes because I'm curious. Excuse me. And if you want to, I'm going to post the update to all these in the morning on the Discord if you want to see how they all ended up in the morning. I don't know how many generations it's going to be, but I'm going to let this run overnight. Um, I just want to see generation 18. Come on, come on. Update, update. Here we go, here we go. Oh, they hit a new record. That means there's more Sutta cows. The Mimi is dying. The Mimi species is dying. All right, let's check in. Who is this little bullish? Who is this little bullish one? That one's mighty bullish. Well, yeah, Sutta cow takeover. I gotta add speciation. That'll fix this. The only way that they'll be able to do this with speciation is if they're really, really, really good. Cool. That'll do it. Let's see whatever remaining comments, and then I gotta skedaddle. I gotta skedaddle. I gotta skedaddle. Okay. Do you prioritize long-term diversity over natural competition? Well, that's what I just explained, right? That's what speciation is going to achieve. It's going to give them all a fair shot at evolving and finding their own solutions eventually. I just joined, bro. Beg you to explain simply what I'm looking at. Sure. Only if you comment that you're still here. That's the only way I'll do that. Good. Yes, indeed. Hey, by the way, I've been a fan of yours since your funny ass videos. That's how you remember me, maybe. Yeah, maybe. I don't know. I've been on the internet for so long. You might be right. Um, okay, you're still here. Okay, cool. I'll give you this rundown and then I'm out of here. So, look, simply put, you want to know. Transition. You want to know what are you looking at. So, I have been having a lot of fun exploring this neural network architecture I've been thinking about for a few years now. And this is it. So, as you know, this is an artificial neural network. It has been an amazing breakthrough that's given us a lot of cool tech over the last decade or two or three. And it just works. There's a lot of different versions of it, but the basic model of it is you just take the input, feed forward it into some neurons that store values in the form of weights, and those weights are then optimized to be able to give you outputs that are useful or valuable, right? And this was inspired by the human brain. Uh, we wanted to create artificial intelligence, and the idea was like, well, we use our brain for intelligence, so why not create something that is inspired by our brain? And the hypothesis proved to be right. And again, we have a lot of great technology from it. However, my grievance with artificial neural networks has always been a couple of things. One of which is they're really hard to understand the black box element of what's going on. It's not impossible, but it's really difficult to understand. And I think that I think that as well. There's a lot of like randomness that is difficult to explain and difficult to extract. Like why certain decisions are made within the neural network. They just kind of have to like accept, right? And so one thing I've been a huge fan of biology for many years now, And every like few months, I just go on these like strange biology benders where for like 3 days straight, I'm just looking at like 16-hour content, 16 hours biology content for 16 hours a day, just like bendering and researching and writing all these notes and whatnot. And I finally like it clicked in my head an idea to try to create a AI that is inspired by microbiology. And that is what this project is. I just named it dot just quickly on a whim. Stands for DNA optimized tasks. And how it works is it's very simple to an artificial neural network. You know, like any function, it has input, it has output. And the black box works like this. You pass the input into the external receptors, and the external receptors then, maybe or maybe not, might activate promoter activation. And this is all inspired by microbiology, how our bodies work, how we have the complex life that you see before you every single day. And the promoters then activate to create proteins, to produce proteins, right? And once those proteins are produced, they then have a chance to bind with internal receptors, and the internal receptors are bound to the output. In this example that I'm doing, there are 4 inputs. There's distance to the left, distance to the top, distance to the right, distance to the bottom. And then in this example, there are 3 outputs: turn left, turn right, move forward. And sometimes the proteins will production will bind to internal receptors that's only goal is to activate promoters. So when that happens on this layer, those promoters are carryover that then will get fed back into the promoter activation on the next run. So there's a bit of a recurring design here as well, which is very much how our bodies work as well. And so you take something as simple as just like how our bodies work, and then you try and design something that's inspired by it, and what you get is this. And it was just an idea. I wasn't really sure if it was gonna work. I didn't know if it was gonna converge ever, but I spent a couple days. I was working on it, and then I came time to test it. I tested it, and it actually started to work. Like the intelligence was, the graph was going up. And I was very surprised. I was like, holy shit, there's no way this is working. And I'm not sitting here claiming that this is like the next breakthrough in AI. I'm not making any of those cringe claims. I have no idea. It's just fun. It's working, so it makes it compels me to keep on having more fun. But what you're looking at is, well, if we go back to this animation here, what you can see is it's 100 different organisms that are all have their own dot algorithm, which compels them to move based on their inputs. And they are trying to optimize as a species on the task that I gave them, which is get as far away as possible from the center. And it's a really simple toy example just to prove that it works. And it's so simple that we can just look at this and intuit what the optimal solutions are. Top left, top right, bottom right, bottom left. Those are the 4 most optimal solutions for this task that you're given. And finally, we can track their progress by looking at something like this graph. You can see that they start on generation 0, and then this pool in particular with a 10% mutation rate, which we tested, which is it was initially 1%. You can see on generation 11 here, they found something, and they really increased their average score by a lot. There are some other generations that still are working on it. I know it's been a lot, but yeah, the whole point of the stream was to try and find this bug specifically that you're looking at, so that I can figure out what to do, how to fix it. And I think that this confirms that the bug does exactly what I hypothesized, and when I had the solution, it should fix it. I think that's everything. I guess the last thing to say is that once I feel like this algorithm is in a good enough place, like it's good enough, we can then test this on like more complex problems and get to watch some really, hopefully, exciting convergence happen with a lot of unique behaviors that maybe possibly is really difficult to get that one-to-one emergence with a neural network. Uh, that's the hope, at least. But this is not good. This is too fast, and it's just gonna stagnate for a long time. I say it's not good, but if you run it long enough, eventually they'll figure something out eventually. But I don't know. Anyways, listen, I love this shit. I'll sit here and talk about this for the next 8 hours. I thank you all for joining the stream. Instead of recreating the brain, you're evolving a slime mold that can solve certain specific challenges. You can look at it that way. You can look at it that way. I don't know enough about slime molds, but I'm essentially trying to create like a bacteria that has very rudimentary functions, and it's given like a really quick timeline to evolve on a certain task, if you will. But I don't even know if that's correct. Have you ever been to the University of Toronto? I think they're big on AI. I'd be surprised if every university is not big on AI at the moment, to be honest. But no, I've never been there. Jay, you the man. J man, you winning? I don't know. We'll find out. That actually helps a lot. Thank you for taking the time to explain to me. It's fascinating. So, what applications do you see for dot in the future? My bad. Fungi creeps me out. Yeah. Well, I think I just answered that. Razvan. I think slime modes act more like a hive mind. Even if yeah. Thank you all for coming out. I love you all. I can sit here and talk about this nerd shit with y'all all day long. Again, I'm posting all the results from these runs in the Discord. Go to Jabrils.com. You can't miss it. It's going to be in the dot channel. If you want to see that, join Discord. I'll post it tomorrow morning. Other than that, love you all. Take care of yourself. All right. I'll see you on another live stream some other day. Peace out.